let's move on to the next lecture, which is part 6 for sources of water. And in this, we are gonna study about the yield of tube well. So let's see a quick recap that uh, in previous lecture we did yield for open well. So for open well, we have seen there was pumping method, there was recuperation test. So for open well, the yield we calculated. And then we saw about drawdown, what's drawdown, and recuperation test. We have done that. So this is what we studied in previous lecture. And what we are going to study today is, like, the question is that can a tube well supply more water than open well? Is this truth? Can it happen? So the answer is yes. And how? So for that we are going to see the tube well yield. So with that we will be able to understand, yes, it provides more discharge, and how it is doing that we are going to see. So in today's lecture we will be learning what is yield of tube well, what are the components of tube well, what's groundwater flow, uh, and then factors affecting yield of tube well, and then we'll be seeing the tube well formulas. We'll be deriving it, kind of derivation. So let's see. So what is the yield of tube well? So it is the maximum quantity of water that can be continuously pumped without causing any excessive drawdown. So it is simply yield is known to be this. Without causing excessive drawdown into the water table, what is the maximum quantity of water that we can get it continuously? So that we know that we call it as yield. Yield can be of open well, yield can be of tube well. So here we like this picture I'm already showing you from last 2-3 lectures. So this is how the screens and strainers are there, and from the aquifer the water goes into this, and from the strainer it strains the water, and then the water comes into the rising mains or the delivery pipe, and then it goes up to the casing pipe, and then with the electric pump we just take it out, right? So this is how a tube well is working. And if I compare it with open well, so for uh, open well gives a discharge of about 5 to 10 liters per second. From open well we can get the water which is 10 to 5 to 10 liters per second. This is for open well. But for tube well, the discharge is around 200 to 220 liters per second. So it's like, I don't know, it's like many a times of, it's like 20 times almost of what we are getting from open well. So tube well discharge is too much in comparison to open well. It's electric, so it's less mechanically operated, that less human intervention is there in that. So tube well is far better than open well, but it is costly, right? So I have already told that in previous lecture. So the construction is something like this. We have screens and strainers. From that the water gets strained and then it rises. Why? Because there is electric mechanism there that takes the water out. Water rises and it goes out of the pump. Okay. So this is how the tube well works. Now see, the topic is how water reaches a tube well. So we have made a tube well. We don't know, like already, like we know that where the water will be there under the ground, how much will be the height or the depth where the water will be there. But how that water is going to come into the tube well? So first, the water is available in the aquifer around the well. All right. So we can see the water is available in the aquifer. Now it moves through aquifer. Now the groundwater moves through the pores of the soil and rock. So there is a movement. Okay. Now it passes through the gravel pack. We have, before putting the tube well, we just apply the gravel pack. Can you see this? This is the gravel pack around the tube well. So this water passes through the gravel pack. So what happens that it will act some kind of screen, right? And it acts as a filter, right? So it acts as some kind of screen or filter. Now after passing through the gravel pad, it comes to the screen. The water reaches to the screen. Now it enters into the screen. Now filtered water entered through the screen and it into the well casing. Now these are the screen, and through the screen the filtered water will go into the well casing. This is perforated screen. Okay, and then this is your well casing. After screen, this in this it will come, and then we have pump. So in this the water is there, it is stored. Now the pump will be used for lifting the water. We need energy to lift the water, right? Water came from all these processes into the tube of the well. Now we have to lift it. For lifting it, we need to have what? We need to have a lifting mechanism. So pump works here. So pump lifts the water. So this is how tube well works. So yeah, and we have groundwater flow towards tube well. So the flow which is the groundwater is doing is radial flow. This we need to remember. The flow is radial flow. And if the groundwater is coming like this, you can see. So previously the water table is this, and the water which is near to the well will reach first here. So the water table will look something like this. It will fall, right? It looks something like this. And water, and the flow is radial flow. It's coming from all around. It is coming from back also, right? It just imagine it vertically. So this is well, and from all over the water is coming into the well. So it's a radial flow, flows towards the well screen from all directions in the aquifer. So water flows radially inward through the aquifer and passes through gravel pack and then enters to the screen, and then it is lifted by pump. So this is how the groundwater is flowing. Which type of flow is there? Radial flow. So this is the one which I was talking about. This is cone of depression. So cone of depression is formed around the pumping well. Okay, so before pumping there was static condition. This is static condition. After pumping there will be dynamic condition. That means the water table will change with the distance. Okay, so this is the dynamic condition. So before pumping the water table is at its natural level, right? And then when pumping start, water is removed from the pump. So water which is coming into the screen, it is removed by the well, and now groundwater flows towards the well from all direction, and then water level near the well declines. So first it will use the water near the well, right? So the water level near the well declines, and it forms a cone shape. So if we see in a 3D, so it will be forming a shape like this. This is the well, right? So this is the well, so it is forming a shape like this, something like this. All right, so this is a cone type of shape. So we call it as cone of depression. We call it as cone of depression. Now the so you can read the key terms here. What's drawdown, what is cone of depression, and what is water table, static level. Water table is static level, and then it is cone of depression. Yeah, so I hope you guys understood this. Now we should see what are the factors which affect the yield. It's same like we were seeing in open well. So that is, first is diameter. More the diameter, more the yield will be there. So diameter, screen length. More the screen length, more the water will be there stored. Hydraulic conductivity, more flow. Aquifer thickness, more water is there, we'll be getting more yield. Drawdown, more the drawdown, that means we are taking more water. Recharge, the how fast the aquifer is recharged, right? So that also affects the yield of the tube well. So now we know that what is yield, how the water is coming into the tube well. Now if I want to calculate how what is the yield of the tube well, so tube well formula for calculating yield, yield, right? So we have two formulas to calculate yield. First we have Dupuit's formula, Dupuit, and then we have Thiem's. Okay, so the very first which we are going to see is Dupuit's. So Dupuit had some assumptions like the is homogeneous, medium is homogeneous, isotropic and infinite. And what else are the assumptions? So the first assumption is this. Second assumption we have that the flow is radial, that we are seeing already. Flow is radial and it's coming from uh, all around the well. So it's radial and it's coming horizontally. So it's radial, horizontal, and laminar. It's not turbulent. So it's laminar, right? And then third one is we have, it's for small elevation. Okay, so for small elevation we need to have sine theta is equal to tan theta. So that means for smaller angle we'll be having sine theta is equal to tan theta is equal to theta only, right? So this is also one of the assumption. So this is how we are gonna move further for Dupuit formula. So let's make the diagram. So excuse my drawing here. So we have a well something like this, all right, and then we have ground level, okay, and then we have water table, right, and yeah, so water table is like this, and then we are taking water out, right? So the discharge is going out and then the water level is dropping. So we have something like this, right? uh, and let's say this is the bottom of the well, right? Right, and so this is the total height, right? This is the water table, and now the water table is this in the well. And let's say we have a influence well, okay, and the influence well's height is h plus dh, and its radius is dx, and its distance from the well is x. So the total distance is x, and initial drawdown is S naught. This is the drawdown of water table. So this is how we have, and yeah, this is the influence well. And yeah, so this is what we have here. Now if I want to calculate what is the discharge in the this dx area only, so the discharge qx can be written as ax into vx. At this, what is the velocity, and at this, what is the area? So this discharge of this dx radius, well, radius of influence is this much, right? And can I write this radius of influence uh, height, which is the area? It is 2 pi x h. Radius of influence total height is 2 pi x h into Vx, and Vx can I write as Ki, and I is nothing but I dH by dx, right? And this is nothing but Qx. So can I take this x term there, and we have Qx. Q is a function of x we take, then it goes upon, and then dx is there, and here I get 2 pi k h dh. Now if I integrate both the sides, I get qx becomes capital Q for full discharge, 1 upon x becomes ln x, and x is nothing but this is the radius of well, we denote it by rw. So x starts from r is equal to rw to total radius of influence, that comes to be capital R. So total radius of influence is R. So we do it from RW to R. And for height, it goes from H naught, initial height, to capital H. Okay. Now, if I integrate, I get Q into 1 upon X is nothing but ln X, and it goes from RW to capital R, and here I get 2 pi k. H is nothing but h square upon 2, and we have to put limit h naught to capital H, and then I get q ln r minus rw. So I can say ln r upon rw, right? And it is 2 pi k, from 2 to 2, the thing, 2 pi k, I get it like h square minus h naught square upon 2. So if I rearrange it, I get q is equal to 2 pi k h naught, h square minus h naught square upon 2, divided by ln r upon rw. So this is what the formula is, and I can cancel this 2 to this, and if I want to change the ln from log 10, so finally I can say q is nothing but pi k h square minus h naught square upon 2.303 log 10 of r upon rw, right? So this is Dupuit's formula, the discharge that is calculated with the help of Dupuit's formula in any unit, meter per second, or in liter per second or meter cube per second. So this is what discharge it is. But one problem is there with Dupuit's formula. So the issue is, oh, yeah. So the problem is that we don't know actually what is the radius of influence. So radius of influence, we don't know exactly where it will fall. We can't calculate radius of influence. So Dupuit formula becomes a little bit restricted. Like from where will we put the radius of influence value? So for this, to saving this, there comes Thiem's formula. So the second thing is Thiem's formula. So for solving this issue, what Thiems did, he kept two wells. So what were the two observation wells there? So he had, uh, so basically in the same diagram, if I put two wells, something like this, one well is here, uh, and another observation well is here with the distance r1 and the distance r2. So he did nothing that much changes, just he kept two observation wells r1 and r2 from the uh, our original well distance. And then what he did, so what we have, so we had one original well and then we had two observation wells. Now from the same method we'll be calculating the things like uh, q is nothing but 2 pi xh ki x, and everything will go on the same case, but I'll not be doing themes in full. I'll be just writing the final formula. So the final formula can have pi k, yeah, and the drawdown, the height from here is for h1 for first observation well, this is first and this is second well. First observation well it is h1 height, and then second observation well it is h2 height, and similarly like drawdown is s1 and s2, right? So the same formula will now become pi k h2 square minus h1 square upon 2.303 log 10 r1 upon r, this is r2 upon rw, right? Or similarly it can be r2 upon r1. You can put r2 upon rw, or you can put pi k h2 square minus h1 square upon 2.303 log 10 r2 upon r1. Now so whatever the thing is given, if you are, if in the exam, if it in the question r2 is given, then you'll be putting r2. If rw is given, you'll be putting rw. R1 is given, you'll be putting r1. So whatever comes, you have to use the formula, right? Now these two formulas are for unconfined. So these are for unconfined aquifers. But if I have confined aquifer, then what will I do? Let's, so if I have confined aquifer, Next is for confined aquifer. Unconfined theory will not be working. So we have, so Dupuit's proposed only for unconfined. For confined, things were modified, and we got finally, I'll be just writing the final formula, which is 2 pi k h. And here, I think, let me just at least make the diagram so you guys understand it properly. uh, See, you will be having the well something like this. It's on the ground, and then you will be having from, okay, here water table will not be there, right? You will be having a confined aquifer, so the water is in this confined area only. Okay, so this is water, this is water table, right? And this confined aquifer is having height h. Confined aquifer are under pressure, right? So original piezometric height will be somewhere like this. Okay, and then because the water is going out, there is some drawdown. So the, so now the cone of depression will be something like this, because this type of confined aquifers are originally under pressure. So if it is under pressure, there will be a piezometric line, right? There will be piezometric surface, and after drawdown there will become one cone of depression, right? So if this is cone of depression, if this much water is there, and this is the drawdown, right? And this is height of water in the well, all right? And if I want to see somewhere here, this is our observation well. So we have, this is h of observation well, and this is h plus dh. This is, this much is dh, right? So this is h plus dh, and this observation well is at a distance x from our actual well, and this much is dx, right? So this is what our setup for confined aquifer is, right? Now let's say, let's derive it. Qx is nothing but ax vx, right? Area into discharge, and then area is nothing but 2 pi x of this observation well, and total height is going up to h, capital H, right? And v is nothing but k into dh upon dx. So everything is going in the same way, and if I uh, integrate, so I get q is nothing but integration qx upon x, right? uh, so I'll be having qx upon x dx, right? Is equal to 2 pi h k dh. So here I'll be integrating both sides, and qx is a function of x, and when it comes out to be as capital Q, which is the full discharge that will come from the well, and 1 upon x will be your ln x, and the limits will be from rw to what, r, radius of influence, and from here the limit will be 0 to, the total depth is, let's say the total depth that comes from the piezometric height is d. So till here this is going on, right? So 0 to d, 0 to d. 0, no, not 0, right? We have this cone, or depression. So bottom height is HW and top height is D. So it's HW to D, right? Now ln will be from RW to capital R, and this will be 2 pi, but see the h here is constant, so it will go out. K is constant. H will be integrated and it will be dh is h, and then d to hw, small hw, and we get q into ln r upon rw is equal to 2 pi h k d minus hw, right? And if I want to put it in terms of q, then it is 2 pi 2 pi k h d minus hw to the power upon ln r upon rw. So this is how the discharge is calculated in terms of confined aquifer. So this is basically what uh, we do for tube wells to calculate the yield of the tube well. So we have, so let's revise like in simple terms. So we have uh, unconfined aquifer, because tube wells go into the confined also, right? So we have confined aquifer as well. In unconfined we had Dupuit's formula, but Dupuit's we were not knowing what is the radius of influence, so we can't put that. So Dupuit's had this limitation. For that, Thiems has one idea to put two observation wells there. So by that, Thiems has created one more tweak there, and then comes the confined aquifer, in which the height of aquifer is fixed, but piezometric height will be different. So for that, we have derived the formula. So this is how we'll be calculating the yield of aquifers. Now, can we move on to one numerical? So let's move on to the numerical. So it's something like this, that a fully penetrating tube well is constructed under an unconfined aquifer with the hydraulic conductivity, the radius of influence, the radius of well, and we have given the initial saturated thickness, and then water level in the well during pumping is this much, and we need to use Dupuit's equation and we need to calculate the discharge. So what was the Dupuit's equation? That was pi k and h square minus h w square upon ln, and yeah, if I need to put log 10, then I have to have 2.303, and we need to have r upon rw. So pi is pi, we know pi, and k is given 30 meter per day, into h square is 18 square minus hw is 12 square upon 2.303 log 10. Rw, radius of influence, is 250 meter, divided by radius of well is nothing but 0.25 meter. So can I calculate it? Yeah. So it comes to be 213 to. So the discharge comes to be as 2454.1 meter cube per uh, day. So the units are, see, you can see it's in day. So I have put in day, and all other units are in meter. So I'll be putting it in meter cube per day. So you need to think about units as well. Like if it is in liters, then you need to convert one thing. This like K is in liter per day, then we need to change it, right? So liter per day, so I need to change it into meter cube. So yeah, this is how you need to focus on your, like, concentrate and take care of the limit also. So this is how we calculate the discharge. And now we have small comparison, which is open well with tube well. So large diameter, it has small diameter, it has low yield, it has high yield, it's shallow, it's deep, it's manual. Possible is there in open wells, but in tube wells, because it's too much into the depth, so we can't take water from here. So we, and its diameter is also small, so we need to have pump to get the water from the tube well. So advantages in tube well is high discharge, 200 liter per second. It's too much, and because it's close, the diameter is small, so the contamination is very less. And advantage is it reaches to the deeper aquifers where that open wells can't reach. So deep aquifers can also be used here, and the land requirement is literally this much. So this much land requirement is there. So it also very small, but limitations are there, that it's expensive. We need to have skilled drilling. Pump should be maintained, okay, and power is required. You can't operate it without power, and it takes a lot of power. So yeah, so today we studied yield, we studied tube well construction, we saw radial flow, we saw cone of depression, we saw formulas, Dupuits and themes, and then we saw both for unconfined aquifer as well as confined aquifer. And in coming lectures, so this is how we have completed our sources of water. I hope you guys understood this. Now in the next topics we are going to discuss about quality of water. So be with us and let's study.